Okay, so welcome back. Now we're going to do this example here. So we have this function cosine 2x equal 1/2 over this interval. So what we're going to do is we're going to look at this angle here and we're going to solve it. And so this, we can look at this as, let's say, theta. Okay, so let's pretend this is theta, and how would we solve this if this was just an angle? Okay, and again, we're going to solve this over the interval from 0 to 2 pi. Okay, and so we're going to solve for x. Okay, so now in this case here, we're saying x is from 0 to 2 pi. Okay, but I'm just doing a substitution here for theta. So what do we know about the angle, the cosine of theta? Well, if the cosine of theta is equal to 1/2, right? If you look at it this way, then we know, first of all, this is going to be in the first or fourth quadrant, the angle. Okay? Now, we also know that this is going to be a 60-degree angle, or pi over 3. Why? Because, again, for our reference triangle, or using the unit and using the unit circle, we know that this is going to be 1, and that's going to be 2, because it's cosine, and that means this is square root of 3, and we have a 30, 60, 90 triangle, whereas theta is across from the middle length side, which means it's going to be 60 degrees. Okay, so we know that one of the angles for theta is going to be pi over 3, and since the other one is in the fourth quadrant, we know that the other one is going to be 5 pi over 3. Okay, and so those are the two angles that we get for theta. Now, but that's not what we're solving for. We're solving for x, which is equal to 2x, which tells us that x is equal to pi over 6 and 5 pi over 6. Now, what else? Well, what if we go, now notice that both of these angles, this is 5 pi over 6, that's in the first quadrant, and 5 pi over 6 is in the second quadrant. Okay? Now, what if I go one more? What if I look at theta and I say, okay, well, let's go 2 more pi. So again, if I look at this, if I go 2 more pi, I know I'm going to get 2 more solutions for cosine theta. So let's think about that. So if I say, okay, well, let's do theta equal to pi over 3 plus 2 pi, and theta equals to 5 pi over 3 plus 2 pi. That's going to give me another solution to this. But then again, keep in mind that this is equal to 2x, right? And if I multiply through everything by 2, then I get x is equal to what? I get x is equal to pi over 6 plus pi, or x is equal to 5 pi over 6 plus pi. And so this is going to equal what? 7 pi over 6, and this is going to equal 11 pi over 6. Now notice, we're still not at 2 pi, we're still under 2 pi. But here's the thing, I've got these two, and I've got these two. Notice that these two are in the first and second quadrant, and this one is in the third and fourth quadrant. Now, if we go one more, if we add 2 pi again to the 2 that we got here, so let's say this is going to equal, okay, so this is going to equal 7 pi over 3 and this is going to equal 11 pi over 3. Now if I add another 2 pi, and then divide by 2 to solve for x, now I'm going to get something that's going to be bigger than 2 pi, and I'm done. Okay, because I can't count those. Okay? So, but notice something here. We know for this cosine function, we know that for any theta equal to, in this particular case, any theta equal to pi over 3 plus or minus 2 pi times k, where k is a constant, or k is an integer, or theta equal to 5 pi over 3 plus or minus 2 pi times k. But what if we, again, all we have to do is, again, solve the equation for 2x, right? Right? And just divide everything by 2, and we get what? We get x is equal to pi over 6 plus or minus pi times some integer k. And this one gives us x is equal to 5 pi over 6 plus or minus pi times some integer k. And so this is what we would use, right? So all we're doing is just solving for the angle and then using the general form, right? Instead of using this, right, for theta, we would just use this for x, and then again we would keep adding multiples of pi until we get to until we reach or go past this 2 pi, right? Now, here's another thing to note. Okay, here's another thing to note. Whatever this multiple is, that's going to tell you how many times you need to, what k needs to be, or how many multiples, or how many times you have to go around. So for example, since this is 2, we're going to basically cycle through where k is 0, right? That'll give us the first one. And then k is 1. That'll give us the second one. So for every multiple, it's going to give us more, oh, how do I say this? If I look at it from this point of view, if I look at it in terms of theta, right, and how many times I have to go around the circle, okay, whatever this constant is, that's going to tell me how many times I go around the circle, okay? So if I go around the circle once, that's going to give me these two, okay? If I go around the circle twice, then that's going to give me one more, okay? So again, the multiple is telling you how many times around the circle you're going, okay? And also how many sets of solutions you're going to end up having. So in this case, we have 2 sets of solutions, okay? Why? Because this is 2. Now if this was 3, if it was 3x, then we'd have to go around the circle 3 times, or we would be finding the first 2, and then we would add, for here, so we would find the first 2, and then we would be adding multiples of pi until we got the last 2 sets, if this was a 3. And so that's how this works. So in other words, you want to look at if it's cosine n times x equals a half, for example. So that means that we're going to have to go around the unit circle n times to find all of the solutions between 0 and 2 pi for x. Okay? Or if you're looking at this, you're going to basically find your first 2 solutions, and then you're going to work your way up to k equal to n minus 1. Okay? And that's it. And so those are the solutions for this particular problem. And let me just verify. So we got, yep, that's it. Okay, have a great day.